Okay, all right. Well, good morning, and we will take a look. Today's notes, I have just kind of handwritten some stuff here. Didn't bother typesetting it. Oh, too much to do. Oh, dear. Okay. I want to talk about multivariate examples of Markov chain Monte Carlo. So we introduced the Metropolis algorithm and the Metropolis-Hastings algorithm, and we did a couple examples showing how it can be used to generate data from some target PDF, and that target distribution, so far was just kind of a univariate thing, and we said, a key benefit or advantage of the Metropolis algorithm and Metropolis-Hastings algorithm is that you only need a function that is proportional to your target distribution, and so we had some kind of function f, and we saw a little application of this on Monday, where the target distribution is kind of like this probability distribution over, I don't know, like letter mappings for some kind of ciphered code or message, and that was beneficial to us to use the Metropolis algorithm, because trying to figure out the normalizing constant that goes into the bottom would have been impossibly difficult, because to get that normalizing constant, you have to sum the numerator across all possible cases, and we have 26 factorial possible letter mappings there, and that just wouldn't have been feasible. But we just needed something that was proportional to it, and so we used the likelihood, and we came up with just some made-up way to evaluate the likelihood of our text. I think we ran through the example, and it kind of worked out at the end where it was able to, starting off at some arbitrary location just by kind of swapping letters as a proposal, it was able to, incrementally improve the letter mapping until it got to a region where the probabilities of the letter mappings were high. And again, it's a little bit of a weird thing, because technically, it's a sampling algorithm supposed to generate random samples from the target distribution, and it does that, but it's effective in terms of deciphering the message, because kind of the letter mappings with the highest probabilities are the ones that are the letter mappings that we're interested in looking at. That was kind of like this little niche example, but a much more kind of common application would be trying to produce samples from a higher dimensional setting. And so here I want to kind of look at a multivariate generalization of the Metropolis or Metropolis-Hastings algorithm. Again, the kind of key difference between the Metropolis algorithm and Metropolis-Hastings algorithm is that the Metropolis algorithm does not require, the Metropolis algorithm requires the proposal distribution to be symmetric, and the Metropolis-Hastings algorithm does not require it for it to be symmetric. And in most of my cases, my proposal algorithms are symmetric, so the Metropolis-Hastings algorithm kind of boils down to the Metropolis algorithm, but I'll just keep calling it the Metropolis-Hastings algorithm. This is like a little picture, and again, almost all of my examples, we already have systems to kind of generate values from these examples. But here, let's say we have some kind of target distribution that exists in 2 dimensions. And so this target distribution has some function, some PDF, and we'll call the PDF P of X. And we also have some kind of function that is proportional to that PDF, some F of X. And again, F of X could be the PDF directly. It could also just be the same thing with a different, without that normalizing constant. So depending on your situation, depending on your application, getting the normalizing constant may or may not be difficult. And in the context of Bayesian statistics, we often have the numerator easily figured out, but that denominator, the normalizing constant, is unknown to us. So it's really beneficial for us to have the algorithm only require something that's proportional to it. All right, so in this example, we're going to say our data exists in 2 dimensions. So each of our x's, our x vectors, are a vector of length 2, vector in 2 dimensions coming from, with 2 real numbers. And the Metropolis-Hastings algorithm in the higher dimensional setting is kind of exactly as one might expect. You start off at some arbitrary location, and we're going to just call that x at time t, and I guess we can start off with x at time 0, t equal to 0. And starting at that location, you have a proposal distribution. The proposal distribution will propose some new location. So usually, so for the univariate case, you just kind of propose something, you either go to the right or to the left of it. And now that you're in 2 dimensions, you kind of have 4 possible, right? You can go north, south, east, or west of it. Or I don't know if that's the right way to phrase where you go, but you start off centered at x at time t, location in 2 dimensions, and then you can go north, south, east, west, or basically anywhere around it. So you propose a new location, and then we use the Metropolis-Hastings algorithm to decide, do we accept that proposed location? And so we calculate a probability of moving, and the probability of moving is basically f at the proposed location divided by f at the current location. And if your proposal distribution is not symmetric, you have to kind of account for that with the Hastings part of the Metropolis-Hastings algorithm, where you have the proposal probability, g of x of your current given the proposed, divided by g of the proposed location given your current location, if it's not symmetric. If it is symmetric, then this part over here just reduces to 1. And so you will get some kind of ratio. Either if your proposed location is more likely, then this ratio is going to be greater than 1, and your p move will be 1. And if the proposed location is less likely, then you will get a ratio that is less than 1. And you will only accept it with that p move probability. So to do that, you'll generate a random uniform value. If that random uniform value is less than p move, you will go ahead and accept the proposed location, and x at the next time, x at time t plus 1, is going to be your proposed value. Otherwise, x at time t plus 1 is going to just be your current value, x at time t. Right. So my hope is that this feels comfortable. It's just this is now a multivariate thing. And obviously, in my picture, I did a 2-dimensional thing, and we could just as easily get a 3-dimensional, 4-dimensional, higher dimensional thing. You just need some kind of function where you put in that vector and it gives you the probability density, or at least something proportional to the probability density. Okay, so that's the multivariate version of the Metropolis-Hastings algorithm. What shall we use for proposal distributions? So 2 very simple examples of a proposal distribution. One is a uniform proposal distribution. So here we're going to say we start off at x at time t, some location in 2 dimensions, and you will propose basically your next two coordinates will come from a uniform distribution in both directions. So you just say my x1 coordinate will come from a uniform distribution centered at x1 at time t plus or minus some constant c, right? So if you start off, if your starting location is, say, the location 20, 20, you'll propose an x1, say, between 19 and 21. And then x2 also plus or minus some constant. Could be the same constant, could be different. And so maybe for some reason you want to go plus or minus 2. And so you'll propose your second coordinate to be somewhere between 18 and 22, whatever it might be, okay? So in this case, we are centered at x at time t, and then basically any location within this rectangle is going to be equally likely to be proposed. And so our proposal PDF is, basically 1/4 times c times k, c being kind of the width, I guess half the width of the rectangle, and k being half the height of the rectangle. And that would be kind of a proposal distribution. This would be a symmetric one. So, the probability of proposing a value over here, in this case, g of x is symmetric. So that's a possible proposal distribution. And again, this generalizes very easily to higher dimensions. You just kind of generate some kind of uniform hypercube, I guess, of some new location. So just take your current coordinates and say, for each coordinate, give me a uniform distribution, generate a random value around that, okay? So that's one possible proposal distribution. Another possible proposal distribution is to use a multivariate Gaussian. So you'd start off centered at your location x at time t, and then you'll have some kind of multivariate Gaussian distribution with some arbitrary sigma matrix. The sigma covariance matrix sigma could be you could have independent ones, they could have covariance, whatever you deem to be I guess a good proposal there, okay? And at least in R, we can generate random multivariate normal values using RMV norm. We also showed, a few weeks ago, how to generate random multivariate normal things that have covariance, kind of using that transform. If you generate two independent normals, you can kind of transform it by multiplying it by some matrix A or V or whatever we call that matrix, and you can generate a random value that way. If you decide your multivariate normal x1 and x2 are independent, then it simplifies things. You can just generate a univariate random normal value for x1 and a random normal value for x2 independently, and that's also fine. And these are just different suggestions as far as how do we propose new locations for the Metropolis Hastings algorithm, right? In a higher dimensional setting. And so x proposed here, you just generate an x1 and an x2. In both of these cases here, the uniform and the multivariate normal, these are all symmetric proposal distributions. So, this G proportion, this G ratio between your proposed location and your current location and whatnot, that just reduces 1. So it reduces to 1. So it's just a Metropolis algorithm, even though it's just a specific case of the Metropolis Hastings algorithm. And so this is a way for us to generate multivariate things, okay? We run into an issue though. And the issue is that as your number of dimensions get higher and higher and higher, the probability of proposing a location that will get accepted gets lower and lower and lower, okay? With the univariate case, let's say our target distribution is the standard normal, centered at 0. And we have this starting location out at, say, like exit time t is 100 or something, right? And I think I showed you an example where we had a terrible starting location, but the Metropolis algorithm eventually found where it was supposed to be. And so if you start off at like 100, okay, terrible location, but you propose something, and when you propose something, you're either going to the right or to the left. And so you might propose a value like 101, you might propose a value like 99, okay? And basically, you have about a 50% probability of getting towards where you're supposed to be, right? Because either half the time you're going to propose something in the wrong direction, half the time you're going to propose something in the correct direction. And so you have about a 50% probability of going in the correct direction. If as you go into higher dimensions though, now you have kind of like a specific direction that you need to head towards, and it gets a little bit trickier to kind of just randomly propose the right direction, okay? So I tried to write a little script to kind of illustrate this. And so let me see if I can make some sense here, okay? So here I'm going to load up multivariate normal. This is going to be our proposal function is I'm going to take my current value and I'm going to just generate a random uniform value between our current value plus or minus 5, okay? So if I'm currently at 20 and I run it through the proposal value, here I generate 20.7162. Let me just show you a couple other things that could happen. If I try it again here, I generated 19.92. I could generate 22.83, 20.43, 15.88. So I'm just generating some random value between basically 15 and 25. And then the acceptance ratio, let's say my target distribution is the standard normal. My target distribution will be the density at the proposed location divided by density at the current location. So if my proposed location is 20.71, my current location being 20, I'm kind of moving in the wrong direction. And so here, the probability that I would accept this proposed location of 20.7 is quite small, is like 10 to the negative 7. So I would not accept this proposed location, okay? I'm going to be working, a lot of times we're going to be working with really small probabilities. So, just like if I do like d norm 55, I get like 0, right? Because, what's the probability that the standard normal distribution would produce a value like 55, 55 standard deviations away from the mean, there's like 0 probability. But, and so, from a computational standpoint, we can't express a number this small, so it just becomes 0. Whereas, if I turn everything into logarithms, I am able to express this value, okay? So the log of d norm 55 is, negative 1500. And so just because we're going to be dealing with really small probabilities, I'm going to be dealing with logs. And so rather than doing the probability at the proposed location divided by the probability at the current location, I'm going to do the log probability at the proposed location minus the log probability at the current location. That will give me my log ratio, or I guess my log difference. And then and I can exponentiate that log ratio, and I will get back the same value. Okay, so so if I just do d norm, I will get 4.64 whatever. If I do the log ratio and take the and exponentiate it, I'll get the same value. And so that's what I'm going to do instead. Is I'm going to be dealing with log ratios. And this is just to and so this script here is, if I'm currently located at 20 and I propose a new random value, what kind of acceptance ratios will I get? Is kind of what I'm asking here. Okay, so I'm going to do log ratios here, and here I'm going to ask what proportion of log ratios are over 0.5. I could also ask, like, what proportion of log ratios are over 1. Okay, and so we get about half of the values that we propose are going to get, will be accepted. Okay, and that's in the univariate case. So this is, I'm just saying, if I start off at 20 and I propose random values about, what proportion of values will I have, like, kind of our acceptance rate be over 1 or just even over 0.5. Okay, and we get, about right now around half or a little over half of the values get accepted. All right, here is the two-dimensional case. I'm going to start off at location 2020, and I'm going to just run it through, I'm going to run proposal through that to get our first coordinate, proposal 2, and then kind of this new proposed location just is going to be, this coordinate. All right, and let's say my target PDF has mean 0, 0, and sigma matrix 1.9, 0.9, and 1. Okay, so I can say, all right, what's the ratio that I would get if I ran it through it, and my I'm sorry, the log ratio here is this, and if I do exp of my log ratio, okay, this is the probability that I would accept it. All right, and again, I'm going to try. This was just for one randomly proposed location. And so what I'm doing here is I'm going to say, if I start off at 2020, the location 20, 20, I'm going to just see, like, what kind of values might I propose using this uniform location, and what's kind of the ratio that I'll, what's the probability that I'll accept any of these things. Okay, so if I ask kind of like, how many of these things will I accept? Now I'm accepting only around 28% of them. Okay, so just going from one dimension, well, okay, I shouldn't say I'm only accepting 28. I'm asking, like, what proportion, I can ask, like, what proportion of these log ratios am I, like, for sure going to accept, asking, because, we said if the probability at the proposed location is higher than the probability of your current location, we're for sure going to move in that direction, right? And so when it's univariate, basically about half the time you're moving towards your target, and you're going to get it right. So you're going to for sure accept the proposed location about half the time. That's what we're getting in the univariate case. In the two-dimensional case, we ask, okay, how often am I for sure going to accept the proposed location? And in 2 dimensions, now we're for sure going to accept only about 28% of them. Okay. I can try this in 3 dimensions. All right, so in 3 dimensions, so once I got to 3 dimensions, I'm just running a little loop to kind of show like my proposed location. So again, my starting location is going to be 20, 20, 20. And so my proposed location is I'm taking each coordinate and I'm just generating a random uniform value around it. So here I'm generating 20.7, 19.9, 22.8. Okay. My sigma matrix that I'm going to use here is going to be a 3-dimensional one with high covariance between each of these things. And I can say, all right, what is here, my acceptance ratio is quite low. And I can just ask, kind of the same kind of question. How often am I going to propose a location that I'm for sure going to accept? Right? How often am I going to propose a location? So if I start off at this kind of terrible location of 20, 20, 20, and I propose a new location in 3D, and I calculate my log, kind of the acceptance probability using the Metropolis-Hastings algorithm. Okay, I run it, and how often do I accept the thing? We can see in 3 dimensions, now the proportion where I'm for sure going to accept this proposed location is now down to like 13%. Okay, so it's almost like 1/2, 1/4, 1/8. And so as we go into higher and higher dimensions, the probability of proposing new locations that have a high probability of being accepted goes down and down and down, because what's the illustration here is okay, I guess if you were playing I don't know, as a kid there was something like hidden somewhere, and you could say, you're getting hotter or colder towards, as somebody's like looking for it, you can say they're getting hotter or colder, right? If the thing exists only in 1 dimension, you're either going to go, you're going to get hotter or colder if you move towards it, colder if you move away from it. And there's basically only 2 directions to go in, okay? When it goes into 2 directions, okay, now it's more difficult to find the correct direction. And then in 3 dimensions, it's even more challenging to make sure you're going in the right direction. Because you could be going the correct direction in the X direction and the correct direction in the Y direction, but maybe the wrong direction in the Z. And in that case, overall, you might not be getting any warmer or hotter. Even if your X and Y are correct, if your Z is in the wrong direction, that might get rejected, and so on and so forth. And so as the number of dimensions climbs, the Metropolis-Hastings algorithm, as good as it is, runs into problems in that we start having to propose a whole lot of things and very few of them get accepted. And so if I bump it up to like the 10-dimensional case, here maybe I'll just do like 4 dimensions. And I ask, what proportion get accepted in 4 dimensions? That drops even further. And then if you try to do something like 10 dimensions, basically like none of them. No, it's almost impossible to generate by random chance to generate a new location that's for sure going to get accepted. Okay, you might get a log ratio that is a little bit that has some probability of getting accepted, but the probability of generating a new kind of location in 10 dimensions where it's going to get for sure get accepted drops down lower and lower and lower. Okay. Here, this is kind of like a more extreme example where in one dimension, maybe only 10% of values get proposed values get accepted, and if you kind of go into 2 dimensions, only 1% of those values. So what can we do if we want to produce random samples in high dimensions? We can't just take kind of our Metropolis Hastings algorithm for proposing a new location as easily as we can. So the solution is to use something called the Gibbs sampler. Okay, let me go ahead and give you your first view quiz answer. And today's first view quiz answer is the letter C. C as in cat. C as in cat. So as we move into higher dimensions, it gets more and more challenging to just propose a new location that will get accepted. So our solution is to use something called the Gibbs sampler. Okay, with the Metropolis Hastings algorithm, it proposes the new location by saying like, okay, your current location is in 3 dimensions. Here's the coordinate, the next coordinate that we want to propose, and it's going to be in three dimensions. Okay, so in the Metropolis Hastings algorithm, we propose all the coordinates of the next location at the same time. We just say, okay, if we're currently located at 20, 20, 20, I'm going to just generate a random uniform value centered at 20, so maybe 19. I'm going to generate, for x2, generate a new random value centered at 20, so maybe 21. And for x3, generate a new random value centered at x3, maybe 18.5 or something like that, okay? And so in the Metropolis Hastings algorithm, let's say our target distribution exists in 17 dimensions. Well, then our proposal location requires 17 coordinates. And even if, say, 16 of those proposed coordinates are in good locations, if one of the 17 coordinates ends up being proposed in a very low probability area, basically the total probability of this entire coordinate of all 17 locations being accepted is going to be very low, leading to its rejection. So that's kind of the issue of Metropolis Hastings in high dimensions, is that you kind of have to all of the locations that you propose, like every single coordinate has to be like better, and it gets really hard to do that. Okay, and so the Metropolis Hastings algorithm, gets stuck very frequently in high dimensions because it's just really hard to propose a new location. So what we do is, in the Gibbs sampler, what we're going to do is we factor this multivariate target distribution into a product of several univariate, possibly bivariate, conditional distributions. This could be analytically challenging. So factoring the multivariate distribution into a bunch of univariate, conditional distributions is how we're going to do it. And so there is a challenge to factor things in the Gibbs sampler, but if we are able to do it, then we'll be able to propose new locations that will get accepted. And so right now we'll just start off with an easy example, and then and I guess next week when we look at some applications, we will look at kind of these problems that lend themselves well to being factored into these, conditional univariate distributions, so that the Gibbs sampler is kind of a natural fit. If doing this, factoring the multivariate distribution into a bunch of kind of product of univariate conditional distributions is not a trivial task. It's if it's just some random arbitrary distribution, it could be quite challenging. But next week we'll look at kind of a class of problems, these hierarchical problems that lend themselves well to this factoring solution. Okay, so the idea is like simple enough, assuming you can do this factoring, distributional factoring. Okay, so let's say we have our this probability distribution that exists in d dimensions, and so every location is some vector x of length d. And what we're going to say is that if this is our current location, okay, x at time t, then what we will do is we will propose our first coordinate based on the conditional distribution of everything else. So we're going to propose our first coordinate at time t plus 1 based on the conditional distribution of x at time x2, x3, x4, all the way up to xd at time t. So let's see. Do you remember the coordinate descent optimization algorithm from 102A? Maybe. So in coordinate descent, we said we're going to hold everything else constant, and then that reduces the high dimensional function down to a single dimensional function. Okay, and we're going to do something similar here, except we're not doing an optimization problem. We are basically going to hold all of the other variables constant, and that's going to turn our multivariate PDF into a univariate PDF. Okay, and so now that we have a univariate PDF, we're going to say, I'm going to generate a random value from this univariate PDF. Okay, now I could use like a Metropolis algorithm and just propose and either accept or reject it. Or if the univariate PDF is simple enough, I could just generate a random value directly from the univariate PDF, right? So let's say if I hold everything else constant, maybe my univariate PDF is like a random normal, and I have a way to just generate random normal values. So that's kind of what we're going to do. We're going to hold all of the other values constant, and we're going to say, okay, what is the distribution of x1? What is the univariate PDF of x1 if we hold all of the other values constant? And once we figure that out, we will generate a random value for x1. And that's going to be the value at time t plus 1. Okay, now that I have a new value for x1 at time t plus 1, I'm going to plug that in. I'm going to hold that constant. We're also going to hold all of the other variables, x3, x4, all the way up to xd. We're going to hold everything else constant. And we're going to say, okay, what is the univariate PDF of x2, where everything else is held constant? And if I do that, once I figure that out, then I'm going to generate a random x2. And then once I get an x2 value at time t plus 1, I plug those into the function. And I said I'm going to hold these constant. So I'm going to hold x1 at time t plus 1 constant, x2 at time t plus 1 constant. We'll hold x4 at time t, and then everything else at time t. And this, we will say, okay, if we hold all of these values constant, what is the univariate PDF of x3? And with that, we generate a random value for x3. Okay, so this part where we're generating a random value for x3, you could use basically any random generation function, inverse CDF, maybe a known, R binom, R norm, or whatever it might be, or even like the Metropolis algorithm, where you have like a separate proposal and acceptance or rejection thing, but just you're going to generate some random value there, and we kind of carry this on forward, and we do this for every single coordinate. As we progress through it, we kind of take our most recently sampled values, we plug those in and hold those constant. Values that we haven't kind of sampled yet, we kind of use the last iteration's values, and we hold those constant. And we say, if we hold all of these other things constant, what is the univariate distribution look like? Okay, so it's kind of if we know all of the values except for the ith coordinate in x, can we figure out what is the can we figure out what the PDF is for x sub I? And if we do, then we generate that. Okay, and so we kind of go coordinate by coordinate, and that's how the Gibbs sampler works. So there's a lot of parallels to the coordinate descent algorithm, but coordinate descent was used for optimization, where you hold everything constant and you say, okay, what is the value that's going to minimize it? And now we're not going to say, I want the value that minimizes it. We're going to basically hold all of the other values constant, and we're going to say, all right, what does my PDF look like? And for this, one-dimensional thing, and then I'm going to generate a value in that one dimension. Okay, so this is an illustration of what this might look like in 2 dimensions. So here I've got this 2-dimensional normal distribution, and we're going to say, okay, I'm going to hold, this is kind of my starting location, and we're going to sample a new. So here's my starting location, x at time t. I'm going to hold x2 constant. Okay. All right, and if I hold x2 constant, I'm going to say, at this location, what is the univariate distribution of x1? If I hold x2 at time t constant. So the idea here is I'm drawing a flat line or straight line at x at time t for x2, and that will reduce this to a univariate PDF. And I'm going to just draw a random value from this random normal distribution. All right, and so here my random normal distribution produced this blue dot right here. So I get a new value from here. And then so at the next, I guess, half iteration here, the next step here, I'm going to hold x1 constant, okay, at this location. So I'm going to use x1 at time t plus 1. We're going to use that, and I say, what is the distribution of x2 if I hold x1 constant? And so it looks like this, and I say, all right, a random location that I sample is going to just happen to be this location right here. And so that's going to give me the coordinate for x2 at time t plus 1, and that's what I'm going to get. Okay, so x at time t plus 1 is going to consist of my newly sampled value for x at x1 and my newly sampled value of x2. And I kind of just iterate over and over and over, holding one coordinate constant and reducing it to a univariate PDF. And then once I get that, I hold that constant and it reduces to a univariate PDF. And we just kind of do this iterative back and forth sampling. And when you do that, then basically every value that value that's sampled is directly from the distribution that we want. So there's no kind of, assuming we're able to sample it directly, every value kind of gets accepted there. Okay. Ooh, we're going to finish a little bit early today. Let me go ahead and give you your second and third view quiz answers, which are the letters B, and A, B and A for your second and third view quiz answers. Okay, and then so next week we will look at kind of a class of problems that lend themselves well to the Gibbs sampler, right? So, I mean, something like the multivariate Gaussian, you can factor easily, but if you have like a complicated distribution, factoring it into a conditional distribution where you say, well, if I hold x1 constant or x2 constant, what is the distribution of x1? That might not be so obvious, right? For multivariate Gaussian, one of the nice things is like if you hold one of the variables constant, it's still going to be the normal distribution in the other direction. But some other joint distribution, it's not so clear cut, and so that's a non-trivial problem. But we will look at hierarchical problems next week, where we can do this kind of factoring into univariate problems here. Okay, so we'll wrap things up here, and have a great weekend. We'll see you next Monday.